In this video, we're going to be talking about an implementation of our randomized selection algorithm. Here, we have a code that will find a random element, partition around the random element, just like we said before. We then compute this quantity m, which is the position of our pivot point in the array. So this m, like we saw with quicksort, will lie between 1 and n. In quicksort, we called this k, but here we've already used the letter k for the order statistic. So if k is the element we are looking for, if this value m is equal to k, that means we found the kth order statistic because m is the order of that pivot element. Now, if k is less than m, that means that our array, after we partitioned it around some point p, this is location s, and it is the mth element. S is the position between I and j, and m is the position from 1 to n. So s goes from I to j, and m goes from 1 to n. If k is less than m, we know that it must be in this left half of the array. So that is this if statement here, and then we're going to be searching the first half of the array. If k is greater than m, then we are in the right half of the array, and we are doing this else statement. There's a bit of a funny thing happening here, and you'll notice that for the first recursive call here, we're going I to s minus 1. That makes perfect sense. We're searching from I to s minus 1, and we go to s minus 1 because we know it's not the current pivot element, and we know that because we already checked if it was. And then we're still looking for the kth order statistic. For that red recursive call, we'll notice that we are doing something funny to our last argument. Our last argument is what element are we looking for? For this problem, we are not looking for the kth element in this set because we've already eliminated m of them to begin with. So we've eliminated all m of those, and we therefore this element here, the first element in the red part, would be the m plus first element. So if we want to find the m plus first element, that would be the k minus mth element in that array. Now, like we have done several times in the past, let us compute the sizes of these recursive calls. So the size of the first recursive call here is s minus 1 minus I plus 1, which is s minus I. And just like we did for our quicksort implementation, we want to re-express this in more useful variables. I can re-express this in terms of m, which I had declared in my code as m minus 1. And for the second recursive call, s2, the size there would be j minus s plus 1 minus 1, which is plus 1 minus s. This is equal to, I'm going to solve the expression for m for s. So I'm going to solve this for s. If I do that off to the side over here, I get s equals m plus I minus 1, which is j minus m plus I minus 1, which is equal to j minus I plus 1 minus m, which is equal to n minus m. These should look very familiar from our analysis of quicksort. We are doing the same thing. We are partitioning an array and then looking at the sides of that partition. So it's no surprise that these two sizes we just computed look almost identical to the quicksort sizes because they are doing the exact same sort of code. So we're going to do a similar sort of thing as we did for quicksort, which is try to understand what would happen with m. So, assuming that we don't enter this if statement here, let's imagine what are the worst possible choices for our algorithm. Well, the worst possible choice would be that we partition the array in a very unfortunate way. So imagine that k isn't equal to 1. If we partition the array, and we're looking, and we get our pivot point there, and it is the first element, then all of the remaining array, all n minus 1 of it, we must search. Similarly for the opposite case. So our worst case here is that m which is random, because it is the position of our randomly chosen element in sorted order, is equal to 1 or equal to n. And the choice there depends on if we are looking for the first or nth element. You would need to choose the other option to guarantee that is the worst case, because it's possible that our order statistic that we're looking for is the first element of the array, in which case m equals 1 would no longer be the worst case, it would be the best case. So m equals 1 or m equals n are the worst case. In that case, let's see what happens. We know that partition takes cn time. So all of the code that is not the recursive calls is finding a random element, constant time, linear time. All of this except for the recursion is constant time. Our recursion relation is t of n equals cn plus t of... Depending on which one we choose, we will either be sorting the last n-1 elements or the first n-1 elements, but it will for sure be of size m-1. To verify that quickly, if we plugged in m equals n here, we would get n-1. And if we plugged in m equals 1 here, we would get m-1. So, we get a recursion relation that we've seen 100 times. I may not have solved it that much, but I've told you what this exact thing evaluates to. This is t of n is in theta of n squared, which is very unfortunate. But that's bound to happen. Our best case would obviously be that we found it on our first go. So our best case would be that m is equal to k, which depends on what order statistic you're looking for. But that would be then t of n equals, partition always takes linear time, plus we make no additional recursive call, so that's it. So t of n is in theta of n. So our best case and our worst case are different, which means we should evaluate our expected case. Now we must examine the expected case. This example is a little funky, so we're going to do this a bit slowly here. We are going to talk about the expected time, and we're going to try to use our definition. So we're going to add up over all possible inputs the probability of that input times the time it requires when we have that input. And the different possibilities for our random variable are that they are at different locations. So this would be adding up over q from 1 to n, the different locations for m, of the probability that m is equal to q times the time when m is equal to q. M is a random element, so it's equally likely that it ends up in any given location. So the probability is 1 over n. And the time required suddenly gets peculiar, though. So let's try and write this down. If we have the sum from q equals 1 to n times 1 over n times the time is cn plus... We have an if statement there, and how do we know which part of the if statement to do is not necessarily obvious. So instead, what I'm going to do is we're going to try to draw a number line here to understand this. We have a number line here for our random variable m. It goes from 1 to n. And when we partition this, let's say that m happened to be here, and that was n over 3. That's just a randomly chosen convenient looking number. And now, if we do that, we have 1/3 of the array over here. And if we have that is on the other side, we have 2/3 of the array over there. So if we're making a recursive call, we are either making a recursive call of size n over 3 or a recursive call of size 2n over 3. And those can be very different depending on where this random variable ends up. So we are actually just going to try to do an upper bound, because like many of these problems we've seen in the past, our hope is that our upper bound is the same as the best case and we can take advantage of that. So whenever we're given a decision like this, we're always going to take the maximum thing in that area. So let's delete this for now and write this down mathematically. We're always going to be pessimistic and take the maximum. So we do less than or equal to the sum from q equals 1 to n of 1 over n times cn plus the max of the two different recursive calls that we could be making. Somewhere we wrote what they were. They are m minus 1 and n minus m, but we're imagining that m is equal to q, so we do the expected time of q minus 1. And then we're finding the max between that and the expected time of n minus m. So it's always taking the worst possible choice when we have a choice between our two recursive calls. And our hope here is that by doing this, we can get an upper bound that is the same as our best case. So we're now going to proceed by doing our normal trick with the number line, where we have 1 to n, and this is our variable m. On both of the flanking sides, as we already analyzed, are our worst case. So these are our worst cases over there. And if we're taking this very pessimistic approach, any cut that is asymmetric, we will always take the larger of the two. So the best possible choice with this assumption is that the cut is in the middle at n over 2. So let's color that blue to emphasize that this is the best case. So that is our rough setup, and we need to come up with some partitions on either side like we did with quicksort. This looks very similar to quicksort. So we have, let's say, n over 3 here and 2n over 3 here. We could have chosen n over 4 and 2n over 4, exactly the same as we did with quicksort. There's nothing special about those, but I chose n over 3 and 2n over 3 so we can see something different. So let's try and compute our expected time by computing various helpful values. We need the probability that we are in our first region over here, or in our last region over here, or the probability that we are in the middle region, which is our optimistic area. So it's probability that m is less than n over 3. Let's say it's less than or equal to. That would be n over 3 over n, which is 1 over 3. Probability that we're in the middle region, which is between n over 3 and 2n over 3. That's again 1/3. And the probability that we are in the last region, which is m greater than or equal to 2n over 3, well, that's also 1 over 3. Now we need the expected times in those regions. So given that m is less than or equal to n over 3, and the expected time given that we are in the middle region, which is n over 3 less than m less than 2n over 3, and the expected time given that m is greater than or equal to 2n over 3. And all we're doing is upper bounding these things. All of them, no matter what we do, we must do the partition method. And then we may need to make a recursive call, and we're always being as pessimistic as possible. So in this first region, that is m equals 1. In the last region, that's m equals n. And in the middle region, it's one of two options. It's either m equals n over 3 or m equals 2n over 3. So, with all this information under our head, we have the expected times here. For the first one, we're searching the remaining n minus 1. For the last one, we're doing the same. And in the middle one, we're doing 2n over 3. With either of our choices, we're either searching the first 2n over 3 or the last 2n over 3. But no matter what, if we're being a pessimist, we are always searching 2n over 3 of the elements. Let's bring all of this together. We have the expected time is less than or equal to 1/3 times Cn plus Et of n minus 1 plus 1/3 of Cn plus Et of 2n over 3 plus 1/3 of Cn plus Et of n minus 1. Let's group everything together. We have Et of n is less than or equal to Cn, because we have a third Cn and a third Cn and a third Cn. We have two copies of a third Et of n minus 1, so that's 2/3 Et of n minus 1 plus 1/3 et of 2n over 3. Now, let's try and do our standard technique when we have a chip and conquer and a divide and conquer and their coefficients are both less than 1. Let's bound the right-hand side further by increasing the argument of that first recursive call. So we change it from 2/3 et of n minus 1 to 2/3 of et of n plus 1/3 et of 2n over 3. Now, let's slide that 2/3 over to the left-hand side, and we get et of n minus 2/3 et of n is 1/3 et of n is less than or equal to cn plus 1/3 et of 2n over 3. Let's multiply by 3 on both sides, and we get et of n is less than or equal to 3cn plus et of 2n over 3. And now, at long last, we're looking like a Foundations 1 problem. Let's do one minor adjustment, which is change 3c to be c1n. Let's proceed by doing substitutions. We can do this as et of n is less than or equal to c1n plus make a substitution, and we get c1 times 2n over 3 plus et of 2n over 3 times 2 over 3 is 2 squared n over 3 squared. Let's do another substitution, and we get et of n is less than or equal to c1n plus 2c1n over 3 plus 2 squared c1n over 3 squared plus et of 2 cubed n over 3 cubed. Now maybe we notice the pattern, which hopefully we've seen stuff like this so many times that this pattern becomes intuitive. This is et of n is less than or equal to the sum from I equals 0 to k minus 1 of c1 times 2 to the I over 3 to the I times n plus et of 2 to the k n over 3 to the k. Let's proceed by finding out what our value of k is. That's 2 to the k times n over 3 to the k is equal to 1. Our base case is 1 because if we're always being pessimistic, once we have one element, we can no longer be any more pessimistic. We've found the order statistic. So if we solved this for k, I'm going to skip the algebra. You can get log base 3/2 of n. Now, let's plug that in, and we have et of n is less than or equal to, factor out that c1n. We're left with the sum from I equals 0. I'm going to leave that as k minus 1 for now. And the inside I can write as 2/3 to the I plus et of 1. Et of 1 is just a constant. Now, to bound that summation, we are going to do et of n is less than or equal to c1n. We bound a finite geometric summation with an infinite geometric series. We have 2/3 to the I plus c. That summation has a nice convergence of et of n is less than or equal to c1n times 1 over 1 minus 2/3 plus c. And now this hopefully is clearly in big O of n. Big O of n. And because of our base case, it must also be in theta of n. Et of n is in theta of n. So, our expected time is in theta of n. One of the only real peculiarities that we did here was the fact that we needed to make a pessimistic choice because of this if statement when we were bounding. I wrote this down in a bit of a formal way here. This was our formal way of writing down our pessimistic choice. That may or may not be necessary, but we need to somehow tell the reader that we are going to be making that decision. So all of this work down here was always talking about upper bounding and making a pessimistic choice, and we maybe approached it slightly differently than using the formal definition like we started. So our selection algorithm appears to be in theta of n for the best and expected case, and part of the reason is that you can expect that the order statistic is somewhere in the middle, whatever that means. It is not near the worst case most of the time, and all you need is a couple of instances of it being like the best case, or at least not like the worst case, to get some real advantages out of this. So we can approximate the median using this selection algorithm, that was our original goal, in linear time for both the best and for the expected case. One unfortunate thing, though, is that for this problem, our worst case was actually worse than sorting it using some algorithm like merge sort, and then finding the order statistic that way. So we don't get strict benefits by making this randomized selection approach. We do get a reasonable algorithm that can do it in linear time, which is pretty good, and it's expected linear time, so that will follow through if we were to use something like this in a quicksort type algorithm.